Welcome. We are discussing about biconjugate gradient method and we are trying to demonstrate the developments over biconjugate gradient method, where the number of computational steps in terms of matrix vector multiplication could be reduced, and also looking into the possibilities of reducing the matrix eliminating the matrix transpose and vector multiplication step. So, on developing that method on a step towards that, we have discussed that the residual and the auxiliary vector in both the Krylov subspace of A as well as Krylov subspace of A transpose can be expressed as two different polynomial functional of A and A transpose. The functional phi is defined for just we have did it in the last class as the polynomial functional phi is for residual and polynomial function pi is defined for the auxiliary vector, and we are trying to develop transpose phase variant of biconjugate gradient method. So, now is the parameter alpha is written as alpha is equal to r dot rj dot rj star apj dot pj star, and we try to write all the polynomial functional in places of rj and pj. Phi j a r0, which is polynomial form of rj, and phi j a transpose r0 star. Similarly, a into pj is pi j a r0 and p star j is pi j a transpose r0. Now, r0 is a vector which is multiplied with the polynomial function. This will be supposed to be supposedly a polynomial of a matrix. So, when we do this product, we get pi j star. So, this vector will come out, and this is the dot product which is between these two vectors. So, this will be phi j star a r0 dot r0 star, and we will get a pi j star a similarly r0 dot r0 star. So, we in order to find out alpha, instead of doing A transpose A etcetera, if we can evaluate the matrix the polynomials, we have to find out the polynomial product of pi j square a and a pi j square a. Also you need to get r0 dot r and multiply it with that. Similarly, the other parameter beta can be found as rj dot rj star plus 1 divided by rj dot rj star, which is similarly if we replace the values of rj plus 1 rj etcetera, we will get phi j plus 1 square a r0 phi j square a r0 r0 star. Now, the issue is that are we actually reducing our steps if we assume some polynomial form of the residue and the auxiliary vector? If we try to look it as apparently as it is coming, that we are not reducing the steps, because doing this, finding this polynomial and doing the square of this polynomial will be itself very cumbersome step. So, what we will try to do is to develop a recursive relation here, so that we really do not have to do all the calculations at every step, doing square, doing lot of operations on a matrix. Rather, we can use some simple recursive relation and find this out. And now, we will look into few variants of the of this method, few of the transpose phi variants of the method. First is the conjugate gradient square method, where r0 the residue norm r will be assumed to offer to behave in a certain polynomial form, and so that the now the residue norm will try to strict it to here. R0 star is the initial residue norm of the left space or A transpose space. For the Krylov subspace of AR0 or while we are solving x is equal to b, for the Krylov subspace related to A, we will try to obtain the residue norm from this part. So, let us see the steps. The BICG step is alpha j is equal to rj dot rj star by a pj pj star, and we update xj plus 1 using alpha, we update rj plus 1 also using alpha, and then we get rj plus 1 star also using alpha and a transpose p. This step we are basically trying to minimize eliminate here, and then we get beta j, and based on beta j we update the pj. This is the matrix vector product. This is because same matrix vector product is used here. So, once we do this we can store this. This is the transpose matrix vector product, and we are specifically trying to eliminate this particular step. The class of algorithms we will try to find will use recursive relations for phi j square a and pi j square a. So, that in alpha calculation I required phi j square a. So, if I can have some recursive relation there, we can probably avoid the matrix as well as transpose matrix vector products. Let us see the steps. This is also to note that polynomials, these polynomials are not computed explicitly, rather they help in formulating the theory. So, none of these polynomials phi j and pi j I am writing down a big polynomial expression and trying to work on them, do lot of matrix to the power j calculations using polynomials etc. We are not doing that. We are not even writing the polynomials explicitly. We are assuming there is a polynomial form and it behaves like a continuous function of a higher order in the space, and we will use this polynomial form to develop a recursive relation and finally get a theory. So, the idea of both the methods will look conjugate gradient squared method as well as biconjugate stabilized method. The idea of these methods is using some recursive relations to make this calculation simple, and for that we are using a polynomial expression of residue vector and the auxiliary vector. So, we seek a conjugate gradient square method, we seek an algorithm where the norm of the residual at jth iteration is obtained as rj is equal to phi j square a r0. And we start with recurrence relations for the polynomials phi j plus 1, that is the next iteration how phi will be updated, is equal to phi j minus alpha j t pi j. This is a recursive relation. These relations actually came out of algebraic manipulations, so that at end we get a nice form and nice way to replace the biconjugate gradient algorithm, keeping the main principle same, that the r and p vectors should be should follow the orthogonality relations that we started with. Similarly, for pi we get another recurrence relation. These are the recurrence relations we are assuming to start with. Now, using this relation recursive relations phi j plus 1 square t I am dropping here because all these are functions of t. So, the functional of t I am dropping here. So, we are trying to develop the relation for the polynomial, keeping it as a function of a single variable t, but same relations will of course hold for polynomials when we will same polynomial when applied over the matrix A. So, phi j plus 1 square is phi j square minus 2 alpha j, just I am squaring this alpha square j square t square pi square. Similarly, pi j plus 1 square is phi j plus 1 square plus 2 beta phi j plus 1 pi j plus beta j square pi square j. So, phi j plus 1 square is related with all the phi j pi j square terms alpha j square beta j square, which will be evaluated in last step if we start with some guess value. Apart from that, there is a product term pi j phi j, and there is a product term phi j plus 1 pi j. So, you have to see the relations from them. Using simple algebraic relation phi j is phi j into pi j is, again we wrote pi j plus 1 is beta j plus phi j plus 1 plus beta j pi j. So, pi j is pi j plus 1 is phi j plus 1 beta j pi j, therefore, pi j will be phi j beta j minus 1 pi j minus 1. So, phi j pi j is equal to phi j plus beta j minus 1 pi j minus 1, which will give us phi j is phi j square plus beta j minus 1 pi j minus 1. So, in case we already know pi j, we can find out, we already know phi j, and we know the last iterations value, we should be able to find out phi j pi j. So, the recurrences can be obtained as phi j plus 1 square is, which was phi j square minus 2 alpha j t pi j phi j plus alpha j square t square pi j square is equal to phi j square minus alpha j t common 2 pi j phi j minus alpha j t pi j square, which is again phi j square minus alpha j t j. Now, pi j phi j can be replaced by this 2 phi j square plus 2 beta j minus 1 pi j minus 1 minus alpha j t pi j square. So, phi j plus 1 square can be evaluated through this recursive relation if phi j square, phi j, pi j, phi j and pi j are known, and also beta j minus 1 alpha j, all these terms are known. So, there is a right recursive relation. If we know the last iterations value, we can calculate it. Similarly, phi j plus 1 pi j, we substitute phi j plus 1, which is phi j minus alpha j t pi j into pi j, and we get a relation phi j square plus beta j minus 1 phi j pi j minus 1 minus alpha j t pi j square. So, if I know again phi j, pi j and pi j minus 1 beta j minus 1 alpha j, we can find out phi j plus 1 pi j. Similarly, pi j plus 1 square is also can be found out by phi j plus 1 square, which is already evaluated, plus 2 beta j pi j plus 1 phi j plus 1 phi j is also evaluated, plus beta j square pi j square. So, we get a set of recursive relations of pi j plus 1 square, pi j plus 1 phi j and pi j plus 1 square here. So, recurrence is obtained for these three terms, and now we will see that how will this help us. Remember, for r and p we have expressed in terms of phi and pi, and we obtain the alpha in terms of phi and pi instead of directly writing it in terms of matrix vector and vector vector products. So, with this recurrence, how things can be helped. So, this recurrence is available is applicable for phi of a single valued function t as well as phi of a phi applied over a matrix A. So, if I know phi applied over the matrix A, phi 0, phi 1 applied over a matrix A, we can find phi 2, phi 3, phi 4, etc. Similarly, other terms. The auxiliary vectors are defined as Rj. Now, in conjugate gradient square method, auxiliary vectors are defined as residual and auxiliary vector Rj is equal to pi j square A R0, Pj is equal to pi j square A R0, and Qj, I define another vector Qj, which is phi j plus 1 A pi j A R0. So, the recurrences can be obtained in terms of R, P and Q, phi square, pi square and phi are obtained, and we can write nice recurrence relations in terms of R, Q and P. So, we develop the recurrence relations for the polynomials, express the residue and auxiliary vectors in terms of polynomials, and now we obtained a set of recurrence relations for R j plus 1, Q j and P j plus 1. Now, if we see why matrix vector and vector vector products were matrix transpose vector products were required to find out alpha and beta. Matrix vector product was required to find out alpha, which is AP. Matrix transpose vector product, if we look into the older BICG algorithm, main BICG algorithm, matrix vector product was required to find out R j plus 1 star, which will be again required to find out beta j. Matrix transpose vector product, right. This is the matrix transpose vector product, which is required to find out R j plus 1 star. Now, if I already get a recursive relation for R j plus 1 star without using matrix transpose vector, that problem is solved, this step is eliminated. Okay. So, we get the recurrence relationship R j plus 1 is equal to R j minus, just substitute the relationships in terms of we substitute the we got this recurrent relations and we substitute it, that phi j square plus 1 R 0 is R j, substitute these relations. That R j plus 1 R j minus alpha j a 2 R j beta j minus 1 q j minus 1 minus alpha j a p j. So, one matrix vector product is still staying there, because from the scalar form of the polynomial form we now came to the vector form. So, one matrix vector is still staying there, the same matrix vector product is being utilized here. However, we did not need to till now we did not need to think of any R transpose A transpose B X product or A transpose P product, all this is A P product. And now we have to see how, what are the recursive relations for alpha and beta, or how to use these recursive relations to find out alpha and beta, because alpha and beta are R, Q and P can be updated. Q is a new auxiliary vector we have introduced here. R, Q and P can be updated through these relations, alpha and beta cannot be. So, the recurrences are obtained in terms of R j plus 1 Q and P, and we introduce a new auxiliary vector u j, which is R j plus beta j Q j minus 1. So, this becomes basically twice of R j, and the recurrences can be written as Q j is equal to u j minus alpha a p j, R j plus 1 is equal to R j plus 1 a j u j plus k j u j, and so q plus u, p j plus 1 is u j plus 1 plus beta q j p beta j. So, there is still I can see there are still two matrix vector products, one is a p j, another is a u j plus q j. However, the matrix vector transpose matrix and vector product, that has been avoided. And once we can get R j, we have the relation that R is equal to B minus A x. So, R j is equal to B minus A x j. So, when we have a relation for R j plus 1, we can get the relation update relation for x j, only the negative sign will be positive here, and this will be divided by A. So, say this is R, I can write R j plus 1 is equal to B minus A x j plus 1, R j is equal to B minus A x j. So, R j plus 1 minus R j is equal to minus A into x j plus 1 minus x j. Using this, we can get the updated relation for x j plus 1 also. So, we get a complete conjugate gradient squared algorithm, where alpha and beta are calculated in same way as matrix vector product. For calculation of which needed a matrix vector product of A p to calculate alpha, similarly q also needed the matrix vector product of A p. R j plus 1, instead of using a transpose matrix vector, R star is not required to, we do not need to calculate the star here, only R 0 star will be sufficient to complete the entire algorithm, because R j plus 1 star has a relationship with R 0 star, which we are exploiting here. And instead of using A transpose, we are using another matrix vector product A into u plus q j. So, the transpose matrix into vector product can be completely eliminated in conjugate gradient square method. And please note that we have used a polynomial based formulation, but never used the polynomial explicitly. That is the beauty of this method. Transpose transpose matrix into vector multiplication is avoided. Still I can look into one significant one serious issue here, that is while calculating Q, I am using alpha into AP. Alpha is calculated using AP. So, the round of error that I am obtaining from while calculating AP is again multiplied with the or added with the round of error I am doing with alpha AP. Similarly, while doing xj plus 1, I am doing x with alpha, which is obtained through the round of error is still there, and then I am multiplying it with q and getting another sort of round of error. Multiplication does actually isn't reducing the error, rather that means adding up of several round of error here. So, there is also a chance of numerical instability because round of error is high. The implementational problem due to a transpose matrix vector multiplication is avoided, but the numerical instability issue is still there. So, the observations are how high round of error due to squaring which is possible. And line 7, what was line 7? Line 7 is Rj plus 1 is equal to Rj minus alpha j a u plus qj, right, and this alpha j is obtained from a matrix vector product. There is some error there. A is again being multiplied with uj plus qj, where qj is also obtained by alpha j aj. So, lot of calculations are involved here, lot of multiplications are involved here, and that also shows that the round of error can be very high and the residual can be computed wrongly in this step. Line 7 may compute wrong residual norm due to twice multiplication of A, which again can be a serious issue. So, it is important to stabilize or smoothen this formulation. This formulation is not also stabilized enough, though the transpose matrix vector product is that step is eliminated, implementational issue has been eliminated. However, the solution is not stabilized, there can be numerical errors here also. So, we go for a new method which is again using the idea of conjugate gradient square method and the principle of biconjugate gradient method, which stabilizes the round of issues due to round of error, which is called biconjugate gradient stabilized method and very popularly known as BICGSTAB method. The method produces iteratively an update of residue vector of a form Rj is equal to phi j a, psi j a, phi j a R0. Earlier it was Rj was only determined by phi, now we introduced another component psi. What is the role of psi? The role of psi is to smooth the function, the error is to stabilize the method. Here the psi j is a new polynomial which is introduced to stabilize or to smoothen the convergence behavior of conjugate gradient square type of algorithm, and this is defined through the recurrence psi j t is equal to 1 minus omega j psi j, there should be psi j minus 1 psi j minus 1 t into r. So, this r is not there, psi j t is equal to 1 minus omega j t psi j minus 1 t. I will rectify this equation in when I will upload the slides. So, here psi j is using something it has a recurrence relation, that means it is related with the last iteration's value, and there is a factor omega which is multiplied with t is updating it, and based on this omega the behavior of psi can be smoothened. Value of omega has to be determined in each step, so that it gives the optimum result to smooth the function psi, smooth the error psi. Let us find recurrence for the other vectors. This is the similar way we did it for the last vectors, psi j plus 1, phi j plus 1, we write the expression of psi j and into phi j plus 1, and psi j phi j. Similarly, we get a recurrence relation. All the recurrence relation now contain along with alpha contain this is the phi j plus 1 and pi j. These recurrence relations are same as the recurrence relations using in CGS method. So, here we are using same relations CGS conjugate gradient CGS recurrence relations. You can check the recurrence relations we have discussed for CGS method, same here CGS recurrence. So, the recurrence relations we have developed for CGS we are using for pi j and we are using for phi j plus 1, and we get a recurrence relation for psi j plus 1, phi j plus 1 and psi j phi j. Why will it be needed to see? The polynomials are chosen to follow same iterative relations as CGS. The residue and auxiliary vectors are defined as R j is equal to psi j phi j a r 0, we have defined that, and p j is equal to psi j a pi j a r 0. Using the polynomial recurrences, a double recurrence of the vectors can be obtained as R j plus 1. The same method we have done for conjugate gradient squared. I minus omega j a R j minus alpha j a p j. P j plus 1 is R j plus 1 beta j I minus omega j a p j. And if we have to use this recurrence relations, we need to find out alpha, beta as well as omega. Once we can find out this, then starting with the first residual and first auxiliary vector, we can find out the next residual and next auxiliary vector. So, the entire problem will be a residue vector finding problem once we can find out the omega j, beta j and alpha j. Alpha can be calculated as original BCG as it involves single matrix vector product. So, the original BCG using the orthogonalization relation can find out the alpha. Beta can be calculated as rho tilde j plus 1. Rho tilde is a new scalar introduced here by rho tilde j into alpha j by omega j, where rho tilde j is phi j psi j a r 0 star, which is phi j psi j a r 0 star, that is r j r 0 star. The dot product between r j and r 0 star is rho j. This is a little involved. I am not discussing it here due to lack of time. It have taken one more session there, but you can look into Yusuf Sart's book here. The finding omega is the next step, and this is complex. Omega is a free parameter which controls smoothness of the iterations. Alpha and beta were related with the biconjugate gradient properties. The conjugate gradiency of the Pj and Pj star in the left and the A space, Krylov subspace, and the conjugate gradient property between Rj and Rj star. Alpha and beta are determined based on this conjugate gradiency property. Omega is a new parameter which is to control the smoothness itself. Let us look into the step of omega. The residual vector is written as Rj plus 1 I minus omega j a Rj aj aj pj, which is we are introducing a new vector Sj. So, the residue vector, the original relation of omega what we got is Rj plus 1 is equal to I minus omega j a Rj minus alpha j a pj. Now, I replace that as Sj and I write this equation. So, what is this? This is finding out the residue vector from the older residue minus some vector Sj. So, I have a older residue vector, I subtracted something from there and then I try to multiply I minus omega j here to find the new residue vector. This is kind of an optimization problem, that finding out the optimal alpha, optimum omega. I talked about alpha which is synonymous here, in a second I am explaining that. Finding out the optimum omega which will give me the faster convergence, so that the new residual becomes 0. This is in a sense very similar to steepest descent algorithm. that find the optimum alpha, find the optimum space descent parameter based on which the new residual will approach the solutions. The new vector will approach the solution, the new residual will go to 0. And exactly similarly, in same way, omega may be chosen as a steepest descent step to obtain the new residual, a steepest descent step here, which gives us omega is equal to Asj trans dot Sj divided by Asj dot Sj, exactly same as the steepest descent algorithm. So, we get the biconjugate gradient stabilized algorithm, where we start with any initial guess x 0 and the initial residual r 0 is equal to b minus x 0, p 0 is equal to r 0. Alpha j is calculated very similar to the biconjugate gradient, original biconjugate gradient method, but now using r 0 only, because r j contains the polynomial of the another a part, phi square a part is contained in r j. R j dot r 0 star divided by a p j dot r 0 star. We introduce a new variable s j, r j minus a alpha j a p j. Using s j we get the optimum omega, and x j plus 1 and r j plus 1 are updated using that optimum omega factor, and beta j plus 1 is similarly calculated, and we again using beta j plus 1 we calculate p j. So, what are the matrix vector steps here? This is one matrix vector step here, this is one matrix vector step here, and we can also see that there is nothing like a residual which is dependent, omega is dependent on Asj. So, it is like omega comes from Asj and then multiplying with Asj, there is no dependence between two different matrix vector products. There are two matrix vector products, but they are not coupled. There is nothing like a alpha Asj type of steps here, step present here. Therefore, the numerical errors are also much controlled here. Two matrix vector multiplication, no squaring, once matrix vector multiplied, again that is not being multiplied with something else. So, no squaring of the matrices, and this is a stable and first iterative solver for any general matrix. This is probably our target, to show that we can have a stable and first iterative method for any general matrix, which can be developed right now, an algorithm can be developed right now and can be utilized in different purposes of solving equations. And we can see that the number of iterations are much smaller for different size of matrices, 16 by 16, 30, 22 by 22, 256 by 256 matrices, to a very high order of accuracy. 256 by 256 matrix, the number of iteration is 269 to 10 to the power minus 11 accuracy. So, number of iterations are same as the number of rows of the matrix of same order. So, we finally obtained a methodology solver which iterates within n steps for an n by n matrix. And we can quickly compare three methods: successive over relaxation, BICG and biconjugate gradient and BICGSTAB. For successive over relaxation, this is a 512 into 512 matrix. A is 512 into 512, and we are not converging up to very high order of accuracy, 10 to the power minus 9 we are leaving. So, convergence is faster. For if we can see for SOR with optimum SOR parameter, it took 44 steps. However, the residue is very smoothly falling down, starting from 10 to the power minus 2, the residue goes to 10 to the power minus 9, below 10 to the power minus 9, and it is monotonically reducing. If I look into the biconjugate gradient method, the residue is reducing, it converges in 25 steps. However, after say after 13th step, 14th step, 15th step, 16th step, 17th step, suddenly residue increases, again it reduces, and again there is some increase in residue somewhere, I guess. So, there is an oscillation of residue, there is no increase, but there is an increase, in residue here. So, if I drop R versus number of iteration, it is coming down like this, there is a numerical instability. in that sense. If the numerical if the matrix is much complex and much bigger, this numerical instability may disturb the convergence of the method. And same we can see for BICGSTAB, the residue is actually falling down. However, there is some oscillation in the residue. So, BICGSTAB probably may be showing a similar method like this, but there is some oscillation in the residue value 1.14 10 to the power minus 3 to 1.49 10 to the power minus 3. Residue increased somewhere, there is some increase in residue, though not this is not as significant as in BICG. So, this is also an oscillatory scheme, and importantly this scheme runs with only high precision machine as well as high precision declaration of the variables in the code. So, to summarize, we got BICG biconjugate gradient or BICGSTAB works for any non-singular matrix. Convergence is non-oscillatory. Convergence is not non-oscillatory. Convergence is not non-oscillatory. There is a, if I plot residue versus number of iterations, there is some oscillation in that. However, the important is that convergence is in lesser number of steps compared to the other methods. So, BICGSTAB is a works for any non-singular matrix, is a not high numerical error method, is a stabilized method and will give solutions in less number of steps. However, there are some oscillations in the residue while converging. Thanks.